yesterday we discussed this idea of TQFT, kind of this linear encoding of manifolds. And today I want to present two kind of modifications. Two modifications. So we will come back actually. So we saw 1D TQFT, basically just vector spaces, and 2D TQFT, which were these kind of Frobenius algebras, commutative Frobenius algebras. So today, first part is let's go back to 1D. But we want to make it a bit more interesting. So the question somehow is, can we make the diagram, which looked like this, more interesting? More interesting, in particular, we wish somehow to distinguish the difference, to make this be different from this. So somehow the idea is to have some kind of an embedded TQFT. So when we draw these pictures, well, there are these zero-dimensional boundary points. And we have the one-dimensional cobordisms, who in this case are just edges. What we had yesterday, we said that these cobordisms are really just abstract manifolds. So today we want to consider these cobordisms as living in some ambient space. In this very concrete setting, well, we want to imagine that these are living in R3. So, zero-dimensional manifolds change. So this is just points. Again, there's some orientation, plus or minus sign, but again, we can somehow put all the plus signs on one side, all the minus signs on the other side. And now the cobordisms now we expect them, or we want them to be embedded. Embedded, let's say, into R2 cross 0, 1. We'll see why we want R2 cross 0, 1, because, well, 0, 1 somehow is like, at time 0 you have like the initial data, at time 1 you have the final data, and you want somehow these cobordisms to be in. And somehow what's important, once you have the embedding, so maybe let's draw some pictures. Typically, what we want to consider are pictures like this. So we have, so now, draw the picture first. So now we have like, this is the t equals 0 plane, t equals 1 plane. And now, for example, I want to draw a picture like this. I would also draw 3 examples. And the picture we can draw is something like this. This. So we want to draw pictures like this. So now again, so this is now a true picture in R3. And well, usually what we did yesterday, we were like reading things from left to right. Now I really want to think about it reading from bottom to top. Because somehow, whenever you have like a two-dimensional object which evolves in time, then very often use the z coordinate. Okay, so we read from bottom to top now. And So in the TQFT, what was important somehow is that things should only depend on the topology. So we said something like, well, whenever you change your cobordism by a diffeomorphism, homeomorphism, then things should not change, right? Like the vector spaces and the linear maps should not change. Now we will change this a little bit. We want to ask that not any homeomorphism works. We want to somehow take into account that we live in some ambient space. So we would consider now cobordisms instead of any homeomorphism we consider what is called an isotopy, isotopies. Tell you what an isotopy is. I will keep these pictures. So an isotopy. So it is a diffeomorphism. Diffeomorphism. Homomorphism. Well, of the space, so we are always in this kind of slice of R2. Let's see. Yes, let's see. Homomorphism of R2 which lies in a one-parameter family of homeomorphisms. Starting from the identity. So this seems maybe a bit abstract, but what it really means is like you have these strings, right? You have these, well, before it was edges, but now it's really kind of a string. You take the string, you can just wiggle it around. You start from the identity, and then somehow, yeah, you can move these things around. But what's important is, yeah, it has to be a homomorphism at every stage. So whenever you have like two things, like two strands like this, well, if you try to cross them, at this point, you don't have a homeomorphism. So actually, I think something's a bit off. It's not really homomorphism of this space, right? Is it? Oh, no, it's okay. Yeah, it's okay. Like, if you try to like do this, yeah, at this point you have two different points which are mapped to the same, so it's not homomorphism. But everything else, like yeah, everything else you can do. Maybe I should say still something. So it should start from the identity, and one more thing, and it should restrict to the identity on the top and on the bottom. You cannot like move these things around. And it restricts to identity on R2 plus 0 and R2. So, well, the definition is very long, but I think it's really intuitive what happens. So let's look at these pictures and let's see whether they are maybe equivalent to something else. For example, this one. Can you maybe change the picture using these isotopies in a way that it becomes more simple? Yeah, exactly. Yeah. You can just take two straight lines. Because yeah, you go over and over again, so you can just push them apart. What about this picture? Can you simplify this? Sorry? No, I think this you cannot simplify. I mean, this is like the simplest version. Well, in this picture we'll see in a few minutes. And maybe one remark is somehow like when you have this kind of pictures, you can really think about actually particles moving in space, I mean moving in this plane. Like they have some initial position and then they have some final position. They might get exchanged, like there might be some permutation, but like the set of final states is the same as the set of initial states. And yeah, and somehow you trace out kind of this time diagram, the movement of these particles you dropped. That was the question, yes?
We always find a representative of those word lines that respects causality, like we can't...
That's a very good point. I want to first define the object and then... Oh no, actually I can make the remark now. No, you
just...
Yeah, I mean, yeah, the answer is yes, you will see it in 5 minutes, yes, exactly. I mean, this, for example, yeah, you can isotope this in a way that whenever you take any intermediate plane, you have exactly 2 intersections, yes. It's like, yeah, so you want to think about these as like particles who move around, and strictly speaking here, at some point you have like a creation, and like you have a creation of two particles, and then they get annihilated here, but actually you can somehow just wiggle things around, and then these particles, antiparticles will disappear. Another question?
Yeah, just maybe something you already explained, but these lines are stick to the point.
Yes.
You can't remove it from the point.
Yeah, so I mean, I will write down the definition, but somehow we will fix somehow the positions of it.
It is fixed.
Yes.
I can't remove it and like unplug it and make it pass through the other line.
No. You start from one of these embeddings, and then for one given embedding, you can start wiggling around, but the isotopy has to fix these 2 planes.
Yeah.
So the object we get from this, from this is called a braid. Well, I think you see why it's called a braid. It's literally what people sometimes do with their hair. Well, typically they would take 3 strands and then you braid them around. What is a braid? Well, N strands. Well, it is an embedding. An embedding, well, I call beta from, well, you have n intervals which are disjoint. I'll write this like this. It's a bit strange because like this set does not have an index I, but it's really literally just you take n copies of this interval and you go into R2 cross 0, 1. And yeah, you fix the endpoints such that whenever you have beta of 0, I, this is literally just the 0 in the ith interval. This we want B to be I, 0, 0 for all I. And the endpoint, well, for the endpoints we allow some permutation, so we say that the set of all endpoints is equal to the set of all I, 1, no, I, 0, 1. Again, the definition might seem a bit abstract, but it's literally just making, like putting formal definitions on these objects. So you have n intervals, these intervals, so you consider them like as disjoint union. So if I ask for embedding, embedding means that, well, you have a homeomorphism, and yeah, you do not allow crossings. And then we will consider grades up to isotopies. Maybe one remark, well, from the TQFT perspective, well, it's actually, from the TQFT perspective, there should be actually also diagrams which look like this. 2 points, nothing in such a thing. So this actually should also somehow exist. So from the TQFT perspective, we should also consider again, things like this. And well, the opposite, kind of creation annihilation. And this typically gives you the notion of what's called a tangle. So it's a slightly more general notion, giving the notion of a tangle. But it's a bit like yesterday. I mean, you can use somehow this duality whenever you have a positive point, you associate V. When you have a negative point, you have V star. And somehow when you have a negative point, then you can just put it to the other side. So in these examples here, actually, well, with this orientation, you have V and V star, or you have V star and V. So somehow you can move the V star to the other side. And then you somehow you come back to the braid setting. And we will see actually braids are much better behaved than tangles.
It was like it is moving. Like, what if you have something like this? How would you move it that would preserve the topology? Like preserve this kind of.
Ah, you mean like these two?
Yeah, exactly.
Like this? Good. Oh, and you mean that it might depend on how you do it, or?
Yeah, because then if you move them like each on the other side, you don't really preserve this crossing, right?
Yeah, but I'm not sure if this is true. If you do this, like this, and then and maybe how you orient them. So if this is V and this is V star, this is V as well. No, this is V and star. So I should argue that you want to move. Yeah, that's. I mean, you're probably right. You can like move it like this or like this. You can undo the twist or not. Well, it's maybe a valid point. Well, I tried actually just to somehow get rid of them. You can just stick to those. That's a good point. Maybe I think something more. I mean, very often in the literature they will speak about tangles, but somehow we'll see why we'll see why we prefer braids. But maybe it's a good point actually. Well, then the remark tells you that there's actually something more, but let's restrict just to the setting. Okay, yeah, now I wanted to make the remark what Kim was saying. The remark is that you can actually use, we can use the isotopies to, using isotopies, we can impose that the intersection between beta and any plane, R2 cross T, that the number of intersections is actually equal to M for all T. So this literally means that you do not have no strand can return somehow. No strand returns. You do not have something like this. It will always go forward in time. It does not exist. And this really allows to interpret the braids as moving particles. And it's even better than this, like you can use the isotopy to put them into kind of this form where at every stage you have just, in this case, two intersections. But of course you have a remaining isotopy. I mean, this does not fix completely the braid. So you have remaining isotopies, and actually these remaining isotopies, they preserve this foliation. In addition, can then consider isotopies preserving R2 cross T. Because, I mean, you could imagine that you have maybe a braid, which is like in this nice form, where particles just move, and maybe there is kind of some isotopy which forces you at some intermediate stage to have this. Yeah, but actually, yeah. If this exists, then there's another isotopy which does not this.
Regarding your previous point, this tangle, I feel like if you just move one point from one sheet to the other, then it's not an isotopy, no? Because your isotopy wants to restrict.
Oh yeah, no. Moving these things, this is not an isotopy. What I said is like, well, TQFT, you have some points like with plus and minus signs. So what I want to do is like you put all the plus signs on one side and all the minus signs on the other.
Sure.
This is how you actually first fix this image. And like every strand goes from a plus sign to a minus sign, so there are as much plus signs as minus signs. So you can really have n points on the one side and n points on the other. And then you have a braid.
Sure. No, so I was...
But from the strict perspective of TQFT, it should actually be possible to have a plus and a minus sign on the same side.
Yes.
And then what the remark was, well, if I somehow change like this initial distribution of points, is it actually, like it's like in this example, for example, you have like 2 points here, but they come with different signs. So if I change somehow this tangle, well, you have a choice actually how to move these 2 points. You can move them like this, or you move them like this. Sure. This will actually give different braids.
Sure.
So probably the answer is like you can associate to every tangle a braid, but this is probably not canonical. So.
Also, you can also have like circles with no points, right? We should also consider those.
Yes, that's true. Yeah, those ones will not see them here. Yeah, that's true. Other question?
Sorry, but I didn't get exactly how you defined a tangle.
Yeah, I mean, I have not defined it. It's not important. I just said like
it's not a place. It's not something like this that you draw on the left. The VV star on the left board.
a tangle is any.
It's like the left board
Is any picture which is which you can decompose in. Well, in either like crossings like this, or these kind of creation annihilation operators.
It's not for, I don't know what you call it, but like when you have, like this image you draw the VV star, yeah, like two crossing with four, these machin. Yeah, I don't know what you call them, you know.
I mean, the definition of a tangle is similar to a braid, but instead of being an R2 cross 0, 1, you're like on a sphere. You're on a sphere, you have two endpoints. I mean, no, you just have, you have a ball. You have a ball, and you embed n intervals inside, such that the endpoints of the interval are the boundary of the ball. Then you typically can get these kind of pictures. Like here, you should imagine there's a ball around. These parts. Yes.
I mean, I still don't see why the ambiguity for the tangle is a problem, because also, so if you have just a crossing in your TQFT,
yes,
then you can also choose whether you want one strand to be in front and one in the back. So you also have an ambiguity here if you want to define your braid, right? Or
I mean, this is different from this. Yes.
exactly.
Yeah.
From a topological perspective, it's the same.
Oh yeah. No, okay, yeah, but I mean, I think here it's like even from the embedded perspective. Even from the embedded perspective, this is different from this.
Yes.
But it is actually natural to consider these as well.
Yeah. Okay, so maybe we can discuss later. It doesn't matter.
So back to this isotopy arrow of time idea. Like in the last example here, it seems to me that you can get like two situations when the first crossing happens first and then the second crossing happens.
This one?
Yeah.
Yeah, this is actually good. This was actually the next point. Like, can you isotope this to a picture which has only outgoing strands?
I mean, my question was more about like if you can do it, you have two choices to how to do it, and like which event happens first.
I think they give the same answer. You can try it. It should give you the same answer. So let's try. Start. So Danilo, do you think it's not possible?
in the last 5 minutes and I can't hack.
Well, I did it, but well, I'm not sure if I'm able to explain. So we have to example you. Well, probably the best would be actually to have it physically in front of you. You can somehow just take this middle part and turn it a little bit. What happens then is that this strand goes, that like this would be the first crossing, so it will be above, like this. Well, what happens next? So now, if you turn your head, now this is to the wait. Yeah, now the other strand goes above, right? It goes like this. And then you have a third crossing where you have still the same. So it goes like this again. And then you're down. I think you literally take this 8 in the middle and you just turn it around.
You're connecting, in the top diagram, you're connecting one at the bottom with the one at the top if you rotate the 8. In the bottom one, you have 2 at the bottom.
Like you change the order of the crossing.
You're changing the order of...
I mean, does the order of the crossing matters, I think?
Yeah. Oh no, the order of the crossings does not matter. I mean, I can push around these strings as much as I want.
But the 8,
Yes.
on the left side, you have a strand going to the bottom and a strand going to the top. No matter how you rotate that 8, there will still be one strand.
No, this strand goes from the bottom to the top. And it goes from the bottom to the top.
Yeah, but if you rotate that, then one will always have to come from the top and one will always have to come from the bottom.
No, I just rotate it, I mean, really slightly, I just take this and slightly turn it. No?
Yeah, but...
Oh, I see.
One is still attached to the bottom.
You're crossing the highest section of the second string, like, so when the string A is at the start, string B is towards its end, and conversely. That's what it means.
Oh, I see.
I don't think it's a problem. You can read the math.
Okay, then maybe I chose an example which is an example of a tangle which is not complete. But this is... this means that something is wrong.
Just imagine pressing one of the lines taut.
Exercise for the reader.
Okay, what this means is probably...
We can try with the cables over there.
What this means is that, I mean...
Actually down. Actually down to try with the cables.
You should build this and really try it out. If it's
you have some
true,
cables.
it means that this remark is wrong. If this remark is wrong, it means that the definition is wrong. And you should actually somehow impose this actually in the definition. You can somehow impose it, right? It gives you somehow n endpoints at every stage. But I'm still surprised. I will be happy to do this.
I think you can, after you turn it, you can use the rhythm master 3 to bring the upper strand down, out the bottom.
Okay, but I think I'm unable to...
If you turn it up, then you...
You think this is right or not?
Yeah, I think so. Because you can then wrap it down, I think. Not sure.
But it's a perfect example of like how not obvious things are, right? So this is why we need like technology, like tools in order to know whether things.
Yes.
We have another way to do it.
Yeah.
You can just imagine one of the strings and you pull it taut so it becomes straight, and then you wrap the other one around.
Oh yeah. I think this is how I wanted to do it. That's true. Okay, yeah. Like you take this string and you just pull it taut. Yeah, that's a good point. Yeah. So you just pull it taut like this.
I think it...
And then what happens to the other? The other one goes below.
Yeah.
Below. Then it goes above. And then it goes below again.
It starts going above.
It's
It's the same problem.
You have to cross upstairs and then go down and go back up. That's the issue we mentioned. Because you see, when you cross for the first time with the right one, you're crossing towards the very end of string A. It's like that's the issue we described earlier.
I mean, what you say, I think it's something like you should do it like this, maybe, but then you can just isotope this.
No, like because you're still like crossing from the bottom. You should be the right string. You should go all the way up, cross, go down, the middle, cross again, goes down at the bottom, and go back up. This is like what the drawing describes.
But you can change the. I mean, you can like. You can slide around everything, no? So you...
I know I've learned here, so...
We will build this during the break and
Do it.
He went
Okay, well, that's a very good example. Okay, so why braids are so interesting, especially compared to tangles, is the following observation.
So you're trying to deform the knot on top and the one on the bottom.
I feel like the discussion will go on for a long time. Okay, so the observation is the following.
There is no so that's
Braids, they form a group. Braids on n strings form a group. So what's the group law? The group law is simply concatenation. Right, you have one braid and another. You can just put one after each other. If I have a braid doing something like this, it's exactly kind of this TQFT idea. You take a braid and you take like a middle class somewhere. It decomposes your object. Something like this. Since your initial, and I mean the final state and the initial state somehow coincide, you can just put one braid after each other. So we have a group law. Well, it's associative, obviously. Putting three things together doesn't matter if you put first these two together and then this. You need a neutral element, a unit. What's the neutral element?
This one, the straight.
And you need inverse. Inverses. This is maybe a bit harder. So let's see first what's the inverse of this braid. Kind of the elementary braid. This one. This inverse.
The symmetric one.
The what?
The one that is symmetric comparing to the upper.
Symmetric one, like you want to turn your head around?
No.
To reflect. If you turn your head around, then it's
horizontal plan. You put it above it, right?
Yeah, like is this?
Yeah, yes.
If you put them together, is this the identity? This corresponds to this picture.
No, not
Yes.
like this. Symmetric comparing to the horizontal upper plan.
I think you mean the means to reflect to the
Yeah, it's the mirror. The mirror is just the opposite. I mean, you don't have much choice actually. It's just this one. Because if you put these two together, you get actually this picture. And you saw that this is isotopic to the identity. And so, well, this is the inverse somehow of the basic building block. But now, actually, what we'll show is that, well, we'll state the theorem that actually these, like elementary crossings, they generate actually the group. Like generators. So you take, well, now we are on n strands. Still, when you have n strands, well, there's still this elementary cross where you just take I and I minus 1, and maybe I and I plus 1, I and I plus 1, and all the rest you just take identity. Everything stays the same, apart from I and I plus 1, which cross. This we call sigma I. Well, then sigma I inverse is the same where you go the other way around. So my convention is that the left goes above. This is sigma I, and sigma I inverse is when the right goes above. So every braid is a product of sigma i's and sigma j inverse. Well, this you should prove, but I think maybe this TQFT idea somehow, maybe it's kind of you start from your brain and you start reading it off. At some point, some things will cross, and they have to be neighbors. If not, they cannot cross. And then somehow, maybe by induction, somehow we can like take this apart and then keep going. And so from this actually fact, we see that we have now inverses for any element of the group. Because if you can decompose your braid in a product of sigma i's and sigma I inverse, well, you literally just invert every element. Probably you have to put it in the other way around. And then, for an example, and then you can see that everything simplifies. For example, if I have sigma 1, sigma 2, sigma 1 inverse, well, just like this. Well, as often in a group, you should first return them, so it's sigma 2 inverse, sigma 1 inverse. Because indeed, if I do sigma 1, sigma 2, and I compose with this, sigma 2 inverse, sigma 1 inverse, then of course things simplify. So to summarize, so we have proven now that braids form a group, because you have a group law, which is associative, it has a unit, and it has inverse. And by the way, it's not commutative. It's not commutative, as we will see. Just like doing a permutation here and then somewhere else. If they are too close to each other, then they're not commutative. En is not commutative. It's not commutative. Like sigma 1, sigma 2, for example, is different. You can draw the pictures and you'll see it's different. Okay, so what we often do in math is when you have generators, well, you can ask about their relations, the relations between these generators. And that's this very nice theorem, to Artin, which tells you what are the relations. Like the relations in the braid group one relation is almost by definition is of course that sigma I and sigma I inverse, they combine to the identity. Sigma I, sigma I inverse is identity, this is almost by definition. Second one is actually sigma I and sigma j, they commute if the indices are far away. Because this literally means that when you cross somewhere, and then you cross somewhere else, but far away, then actually you can really just wiggle around things and change the order. Doing this later. Do this first. So this is not surprising. The surprising, the really nice relation is this one. Famous relation called the braid relation. And you really should draw the picture, like I give you some minutes to draw the picture and to verify that they're indeed the same. yeah, just draw maybe sigma 1, sigma 2, sigma 1. Because anyhow, I mean, if you change the position, it's just a kind of a translation.
Are these relationships enough to describe the whole group?
Yes, yes. The relations, actually the theorem somehow says that of course there are some other relations, but they're just conjugate somehow to these. So this is a full list of they generate the set of relations. Yes.
There's a question here.
We're doing an exercise.
Yeah, like draw the sigma 1, sigma 2, sigma 1. We want to see that this is equal to this.
We might have proved that like this is false. The one on the left. Maybe no.
No, I don't think so. No, nothing I have drawn is this. I think no.
No, but like we might have like I think we have a proof for. I think I have a proof for the fact that like we cannot make this one like fully increasing.
Ah, okay. Probably my definition of a braid is more.
But like maybe I don't understand the definition, but like we have. Like this is the strand 1 and this is
I mean, the order is different. I mean, you could imagine that one gets crossed.
Like if you start from 1, cross A, then you come.
Yeah, sure. But it's such a
if the strand 1 is clean filling, then maybe then Y is
okay, then they get this.
I think that's the way.
So you can't pass through each other.
Yeah, I see.
That's good. Same thing.
Okay, so let's draw these pictures.
Je pense que la preuve que ça marche.
So sigma 1. Sigma 1 is this. Sigma 2. I take this.
Yeah, this is true, but
Like I think all I said.
So the one that goes from right.
yeah, okay, I proved it.
And sigma 1 again.
I don't know. This is the day you prove something.
Sigma 1. Sigma 2. Sigma 1. And similar picture.
You'll at least be able to tell You'll at least be able to tell you.
So I start now from sigma 2. Then I do sigma 1. And, well, it's not that obvious that they're the same. There's an isotropy.
It makes sense to me. Just pull them apart in like the third dimension and you just like rearrange the order.
Yeah, kind of. Or
Because they're all on the same level in this.
yes, yeah, exactly. For example, this one is the one which is on top of everything. So you can actually like put these two below. Like, so you just take this and you put it above this crossing, and what you get is exactly this.
Right, master 3.
They're somehow independent of each other.
Yeah, it's true. Yeah, exactly. You have a top layer, a middle level, and a low level. Exactly, and you can wiggle things around. So somehow showing that this is indeed a relation is not that hard. What's really hard and what's really the hard somehow of the theorem is that there are no other relations. Cool. So we know somehow what the group looks like. It has generators, it has these nice relations, in particular the break relation. Some more remarks. There's of course, as I already mentioned, there's a link to permutations. Like you have this braid group, and every braid, just looking at like the endpoints, gives you a map to the symmetry group, the permutation group. So it's literally you look at how the initial points get permutated through the braid. And so this is, and the fact somehow which is not difficult to show is that this is a group homomorphism. For example, the identity map, the identity, of course, is the identity in the symmetric group. But there are, of course, there are much more braids which are sent to the identity. Any braid where strand 1 goes really back to strand 1, and strand 2 goes back to strand 2, for example, this one. In this picture, strand 1 goes back to the first position, and strand 2 goes back to the second position. This is typically an example of an element which is in the kernel of this map. So the kernel of this map, name? No. The kernel, elements of the kernel are called pure braids. Just as a remark, more or less, because we'll not really deal with them. But yeah, I mean, in my definition, there was kind of this. Yeah, I erased the definition. There was kind of this fact that, well, we fixed the positions of the zeros, like the initial, the starting points, but for the endpoints, we had kind of this fact that there's a set equal to another set. If you want somehow to impose that every endpoint of the interval goes to the right position, then you have the definition of a pure braid. So let's keep maybe the pictures, because we still have to discuss them.
So is a pure braid just one that's isotopic to the identity?
No. It is a subgroup. It's a huge subgroup of the braid group. One element is this one, sigma 1 squared.
Oh, okay.
Yeah, let's give an example. So sigma 1 squared is in, well, often it's called P2, but sigma 1 squared is not the identity. But it's actually a very good remark. What is P2? What is the group? Just two strands. It's isomorphic to a group you know very well. Just have one generator, just sigma 1, and there's no relation whatsoever. Just Z. Because the elements here are just sigma 1 to some power. And this power can be positive or negative. So it's literally the integers, and also like if you multiply sigma 1n to sigma 1m, well, you get sigma 1n plus m. So it's really like it's an additive group. And so the pure braid group, this is, well, P2 is then isomorphic actually to 2z, or the even integers. But, well, this of course is isomorphic to z again, but yeah.
Just a curiosity.
Sorry?
Since the group is finitely generated, do we have some sort of canonical form for the elements of the braid group?
Yes, there is like a way of braiding any braid to put a braid in a canonical form. Yes. But I think, it's not that canonical. I think you have to fix something, some order. One more remark before going to knots and links. For those who are more into topology, the others you can ignore it. But Pn, pure braid group, is actually the fundamental group. Fundamental group of Cn. So Cn is the configuration space. Configuration space of n points. So it's simply x1, xn points in R2, such that they are different. So you take the space of all n tuples of points in the plane, which are 2 by 2 different. This is some topological space. So what is pi1? So pi1 means like, well, this space is connected. You take some base point, so some initial situation of these points, and then moving around in the space means exactly this kind of moving of particles. And well, P1 means you look at loops, so you want to come back exactly at the same position. So you have exactly this idea of a braid where every point goes back to exactly the same position. So you have pure braids. But yeah, this gives you like really a nice interpretation of these groups in topological terms. Like fundamental groups, they are groups in particular. So we have another proof actually that Pn is a group. And yeah, if you really like Bn, and actually we do, then this is the fundamental group simply of the quotient. On this configuration space of n ordered points, this is the configuration space of unordered points. So yeah, again, if you don't understand, or if you don't know what a fundamental group is, it doesn't matter. Just for those doing topology, there's like nice topological interpretation to this. Like, I think physicists, they really like this idea of moving particles, and well, the exact analog mathematically is exactly this kind of fundamental group in some space of configurations of points. Questions? I mean, it's really kind of a crash course of like these very nice objects, braids, links, knots. On the one hand side, they are really intuitive, so actually I think you all have a good intuition what they are. Yeah, so it goes a bit quickly maybe, but we'll soon see the appearance of the TQFT. We need one more ingredient, which is the link between braids and knots. Well, link, connection. So there's a procedure which is called the closing procedure. Closing procedure of a braid goes as follows. You take a braid. I'll just draw it as a box. So you have these end points and these beginning points, starting points. And what you do is the following. So the result I denoted by beta hat. So you take this beta, you add, somehow you connect the bottom to the top, like this. So let's do some examples to see what this gives. Let's see, for example, what happens if I take the identity on, let's say, 3 strands. I have 3 strands, and I do the closure. I close. But still, we have this idea of isotopy. So this is still a picture in R3. So what do we get? We get 3 circles, which are, each circle is not itself knotted. It's something, it's really just a circle. And the 3 circles themselves, they are not knotted themselves. It's just three circles. Unknotted. So what happens to sigma 1, seen as a braid with only 2 strands? This one. Of course, the closure is easy to draw. But what is it topologically?
Maybe a strip.
It's really a one-dimensional object. Yeah, I mean it's true. Like if you add in this it's a Möbius strip, but you should really think about just this one-dimensional object.
It's a loop.
It is a loop, yeah. So it's just a circle. But can you use isotopies in order to simplify the picture?
I have another name for it. You didn't give it, but
It's just a
it's
circle.
R1.
Yeah, it's just a circle. It's really just a circle because, well, somehow, if you really imagine it in front of you, you can somehow flip these two, and then. So this is really just what we call the unknot. It's like the simplest possible knot. Maybe one more example, and then I will give the definition what actually all these objects are. These knots, what is it exactly? So. The last example you can already think about it is sigma 1, sigma 2, sigma 1. I draw the picture and try to simplify it and see what happens. First question is maybe how many connected components do we have? 2. We start here. Yeah, I come back, but then this one is another one. Yeah, there are 2 connected components.
You get 2 entangled circles. 2 entangled circles.
Yes, exactly. These are actually one circle like this, and one circle like this. Yes, it's called the hop field. Yeah, it's probably not obvious, but I mean, if you would really literally put this with some string, and you will see that you can. I think this loop, for example, you can like untwist it, and then you have just these 2 crossings left, which are these 2. Okay, so let's give a definition. What are these objects? We get. So the object is called a link. A link is the following. A link is a value of n copies of the circle. So it's a bit like before. Before we had intervals, now we have a circle. So S1 is the circle. So we have n disjoint circles, and we embed this into R3. And we consider them up to isotopies. Consider up to isotopies in our linear. And if n equals 1, if you just have one connected component, then we call it a knot. So you literally, when you lace your shoes, well, you do some kind of a knot, but what we do in math at the end is you close the knot. Yeah, I wanted to show this. So literally you take, well, this kind of thing, and then you do a knot, well, something like this, but then in math, for some reason, we close it. We close it, and then we call this the knot. But you could imagine that you have maybe several objects of this type, and then you can knot each of these objects, and you can also knot them one into each other. And at the end, considering up to isotopy means that I can wiggle things around. And even like if I don't knot it at all, or unknot it, if I just close it like this, well, I get this famous unknot. But even this unknot, I mean, I can wiggle it around, can do like some stuff. And if I just show it to you like this, you might not be even able to decide whether this is the unknot or not.
I cannot knot.
It's not obvious that I can just do this, right? And then comes the knot again. So somehow the question of like having different, like, well, first question is like, can you classify all knots? This is still an open problem. It's very, very hard. But even like given some concrete embedding, deciding whether this is the unknot or not, deciding whether it's the unknot is also an open problem. And I'm not sure if it's proven that it's NP hard, but it's not something difficult.
Sorry, can you just go down the blackboard a little to see the other?
Yes. And so here what happens, you have these intervals, you have these n intervals. When you close the braid, well, then actually every interval becomes a circle. Well, or maybe several of them get connected. So in the worst case, you get a link with n components, but you might also get maybe just a knot. It really depends on the braid. Like here, for example, we had some examples like here you get just one connected component. So somehow deciding how many connected components you get, it's really about the underlying permutation of the braid. If you take a pure braid, for example, then when you close the pure braid, then you're actually sure that you will get n different components. Okay, based on this notion of braids, knots, yes.
So this closing procedure, it's always like rightmost point to the lower one.
I mean,
because otherwise it's kind of arbitrary.
Right, or going to the left is the same as isotopic.
Yeah,
but
you don't do crossing.
Yes, I mean there's no extra crossing, and like the coordinates here were like I00, 0, and on top it's I01, 1, so you put these two i's together.
If you were to cross, you would just modify the B, beta. Yeah, crossing and the sure, I agree. Yeah.
More questions? There was another one. So there's this very nice link. I mean, there's this nice map between braids and links. Well, actually, maybe I can state it now. Why not? There's a theorem, Alexander, which is not me. It's James Alexander. I think it's from the 20s. It's kind of old. It says that this map is surjective. Like if you take the union of all braid groups and you consider the set of all links, which is this closing procedure, then this map is surjective. It's very nice. It means that any link, I mean, there are many, many links. The classification is very, very hard. But any link can be obtained as the closure of some braid. And somehow, why is this so important? Because we have seen that braids, they form a group, but links and knots do not. Links and knots do not form a group. So this is really why we like braids, because braids are much nicer behaved than these other objects. Yes, question?
Yeah. To do that, people actually use what's the name again? Braids to study them, or are you?
Oh yeah, sure. I mean, you will see. We will construct. I mean, using TQFTs, we will construct link invariants from exactly this closing procedure. Yeah. So last ingredient before going to TQFTs, or maybe before going to the break, we'll see, is the following theorem. Well, actually, one thing we have already used without really saying it is that, well, all these objects, these links, they live in 3 space, in R3. But whenever I draw them on the blackboard, well, I use some kind of projection. So this is called the knot diagram. But of course, when you have one link, or one knot, well, if I project it like this, you will see it like this, but if I do it this, then there's another projection. We can sometimes just change the orientation, or, I mean, there are many different projections of the same knot. And there's a very nice theorem stating, like giving you an if and only if condition when 2 diagrams are the same. 2 knot or link diagrams. So again, a link diagram is just a projection of some knot. Represent the same link if and only if, this is why it's so strong actually, this theorem, if and only if, they can be connected one to each other by a finite number of elementary moves. Well, if one can be obtained from the other, with a finite number of the following moves, there are 3 of them. There's Reidemeister 1 move. Looks as follows. Whenever you have a small loop like this, then this is just an entity. You can just literally take this small loop and untwist it. The Reidemeister 2 move is something we have actually already seen. Kind of this braid. When a strand goes above and again above, then you can just undo it. Reidemeister 2. And let's put the Reidemeister 3 move here. Reidemeister 3 move is as follows. You have a crossing. And some third strand which is just behind. And this is actually the same as somehow, since it's behind, you can just move it to the bottom and you get this picture here. So again, Reidemeister 1, you can undo these small mini loops. Reidemeister 2 is pulling apart 2 strands, where one strand is just above the other. And Reidemeister 3 move, somehow 1 is about 1 strand, 2 is about 2 strands, 3 is about 3 strands, and 3 strands is literally just when you have 3 strands on 3 different levels, you can actually move them around. Kind of, you see a little bit this idea of TQFT, because like you have link diagrams. Well, now somehow you move them around in the space of link diagrams. You move them around using isotopies, but somehow you can decompose an isotopy in elementary pieces. The elementary pieces are these 3.
So how does the link diagram differ from just a link? You're just drawing it
Like
On the plane, yeah, literally on the plane.
And on the plane, like specify like.
Yeah. Like on the plane, I will do this in order to specify which strang in R3 is above.
It's actually just a link. There's a difference.
Well, I mean, I think, yeah, we will really do somehow, we make the difference, but there's not much difference between link diagrams. One small remark, actually we have already seen R2 and R3. Right? R2 corresponds to a relation in the braids. It just tells you that sigma I inverse is identity. Reading this as a braid, you have sigma I, like sigma 1 here, and then you have sigma 1 inverse. And do you recognize R3, this move? I have drawn it not like braids, but actually you can put it in braid form.
Braid relation.
It's exactly the braid relation, because we had this discussion before when we saw the braid relation, we said like one of these braids is actually just very like on the bottom, then there was a braid in the middle and a braid on top. It's exactly this kind of situation here. So this exactly corresponds to the braid relation. So, I mean, I think we don't have time for the exercises, but I would really invite you to look at exercise 3. So now, somehow, how can we use these elementary moves, these Reitermeister moves? So, links and knots are very complicated. Even like deciding whether they are the same or not is complicated. So we try somehow to associate some easier thing to them, like either some number or some polynomial. And we want that these algebraic objects associated to a link, well, we want them not to depend on the isotropy. I mean, they should be invariant under the isotropies. And since you can decompose an isotropy into these 3 elementary ones, if you give me a not invariant or link invariant, actually it's, in order to show that it is an invariant, it's sufficient to like just show that it's invariant under these 3 moves. And now we have seen, I mean, we are more interested in braids. Well, not particularly, but well, another way to get not invariance is to use this closing procedure. And so braids are better behaved, so they're like you can easily come up with like braid invariance. But when you close, different braids can give you the same knot or the same link. So you can ask the same question, like can you decide whether 2 braids give the same link or not? And there's a similar list of moves, elementary moves, and this is exercise 3. They're called Markov moves. Maybe I can just draw the pictures, and then we do the braid. Markov moves, they look like the following. Markov moves. So there's M1 and M2, that's just the pictures. So M1 looks as follows. So you have your braid, B, beta, and you replace it. Well, it should look like this actually. It's about closures. So closing a braid beta is the same, this is Markov 1 move, as conjugating beta by some other braid gamma and then closing. And the second Markov move is you take beta, you add a strand. This is the same as you add a strand. You take the last one in beta and you cross them. The others you keep the same. And then you close. Close here, close here, close here. These are the two Markov moves, and it's not too hard to see that these give the same links. Well, this is the exercise about, and the hard part, which is not in the exercise, which is the theorem of Markov, is that any two braids which give via the closure the same link are connected by a finite number of these links. So the idea will be to construct some braid invariant, which in addition is invariant under these two moves. And then you get no invariants, link invariants. Questions? Still have 5 minutes, and we have started late. And I have much more to tell you.
So is gamma purely arbitrary, or is there any restriction on it?
Yeah, no. I mean, it's in the exercise, right? It's for all gamma. It has just to match the number of points. So if this is of n strands, then gamma is also n strands. Okay, so first we did the construction during the break. So you can, if you want, come afterwards and play with it. So yeah, we figured out, and also with some other people who draw convincing pictures, that indeed this is not a braid. This is not equivalent to this. So this was wrong. So if you take the definition of a braid, there was the definition, and then afterwards there was the remark. Actually, the remark is somehow part of the definition. Like a braid, by definition, is an embedding of n intervals such that at each time slice you see n intersections. It's really part of the definition. And also the isotopies you consider, they also preserve this structure. So it was my fault. By the way, from this topological perspective, seeing them as fundamental group of configuration space, actually you also have the same thing. Because when you move around in this configuration space, at every slice, at every time step, you have exactly n particles. I thought that maybe with the isotopy you can actually get rid of this constraint, but apparently you can't. So this is truly a tangle, which is not a braid. With this being said, we can move on. So we'll stick to braids. We can forget a little bit about tangles, even though they're apparently quite interesting. And now we want to do braid invariants. From TQFT. Or kind of this embedded. Okay, so the starting point is pretty much the same. So we're in 1D. So the boundaries are just points. So points still the same thing. So this is some vector space. And now we have these kind of positive points on the boundary, the other points on the top. So we have as embedded cobordisms. We have these braids. And now remember, the idea of TQFTs is to linearize everything, to get a representation as matrices. So we want now to use these braids, we want to read the braid, now from bottom to top, and we want to associate a matrix, a linear map to them. So if you have an element beta n, we want to associate a map. Well, it's a map from n distinct points. Well, let's write it once more from left to right. So every point gets a vector space V. Since the points are disjoint, you have a tensor product. So if it's you have n strands, you have n tensor products, and you have a linear map to the tensor. So a TQFT is exactly giving this assignment. It gives you for every braid such linear map. And the idea of TQFT, you have this kind of reading thing, so you can decompose these complicated braids into elementary braids. And we've seen that actually there's basically just one elementary braid, which looks like this. And so this should correspond to some map, which we call R, and it goes from V tensor V to V tensor V. Basically, the TQFT gives you two things. First is the vector space, so you just the dimension. And the second data is this R. Because, well, why is this everything? Because, well, first thing is if you take the braid, the opposite braid, the opposite one, this corresponds to, well, R inverse. So, well, there's one thing that R has to be invertible. So it's a linear map. It's in GL. It's in GL. B. Well, and then of course we have braids which have more than two strands. But actually, what happens if you take our generator sigma I? So sigma I looks like this. Just this crossing between I and I plus 1. This, what you associate to it, well, you just associate identity on V tensor R, and then identity on N minus I plus 1 or something like this. N minus I minus 1, I think. Thank you. You understand? You have identity here, R here, identity. In this object, I will call it R index I plus 1. To be precise, the TQFT, it gives you all these R index I plus 1. But somehow the true content is just this one matrix R. It just depends where you put it in the space. But now, so we've seen that these sigma i's, they generate the group, but they have relations. So these relations, they will give us some relation on this matrix R. By the way, there's like a very inspired name. This object is called an R matrix. So what really defines an R matrix is one relation, which is the following. So this matrix R has to satisfy the following relation, which is a famous relation. It's the following. It's R1, 2, R2, 3, R1, 2 equals R2, 3, R2, 3. And this is exactly what is called the Young-Baxter equation. So it's an equation on what? It's an equation in matrices, invertible matrices in V tensor V tensor V, so in V tensor 3. And probably you see why. So this relation exactly corresponds to the braid relation. Braid relation sigma 1, sigma 2, sigma 1 equals sigma 2, sigma 1, sigma 2. Sigma 1 is exactly the braid which swaps 1 and 2. Sigma 2 swaps 2 and 3. Sigma 1 swaps 1 and 2 again. And that's pretty much all. this elementary crossing, you associate this matrix R. If it's the negative crossing, it's R inverse. So in the theorem of Artin, there were three relations. One is sigma I inverse is identity. This is automatic, it's just R inverse is identity. And then there was one more relation, which is this, whenever your two grades are, whenever your two crossings are far away, then these things commute. We have this sigma I, sigma j, equals sigma j, sigma I, if I minus j is far away, and this is automatically satisfied by these matrices R, I plus 1. Simply by looking at the definition, like if you combine identities with some matrix R and some identities, and you compose it with something which is of the similar form but where this R is far away, then you can simply commute them. So the only interesting relation, the only non-trivial relation in the braid group is this braid relation, which in general reads sigma I plus 1, I. In general it reads this. So actually R has to satisfy this relation with I plus 1, I plus 1, I plus 2, and so on. But literally what happens, like you just have identities everywhere. The only interesting part is exactly this. This is why you have this one equation, which has to be satisfied. So maybe to formulate it in slightly different terms, if you want to construct such a TQFT, you have to give me a vector space and an R matrix. Like a matrix that goes from B tensor B to B tensor B is satisfying this relation. Questions on this? So now I will give examples of R matrices. No question? Well, I'm sure that you know one example, the easiest example. Easy example of such an R matrix is whenever you take what we did yesterday. Literally, you take TQFT where actually these crossings don't play a role. So it's the map from V tensor V to V tensor V, which literally just swaps the elements. Swap. So this is one example. You can check that if you take three objects, these three, I don't know if you will see it, if I take these three objects here, three colors, and I first exchange these two, then these two, and then these two. Actually, I just turn them around, and if I first change these, and then these, and these, it's the same. So just swapping things around satisfies this relation. So in this sense, yeah, we have somehow recovered what we did yesterday, but of course there are more interesting examples. So in particular, in this example, R actually equals R. So crossing like this or crossing like this does not change. Okay, so let's go for a more interesting example. So a more interesting example is, well, the smallest interesting case is when V is C2. If it's only one-dimensional, it's too trivial. So let's fix a basis, 1 and 2. And then define R as follows. So R will map, so it's sufficient to define R on a basis. We'll just define it what Vi, Vj goes to. So it is a swap. But then you add something. You add actually the identity somehow, but with some coefficient. So if you have here, I'm not summing over I. This is literally ij. And there's this formula for epsilon ij. So it's Q minus Q inverse if I is equal to J, Q minus 1 if I equals J, and 0 else.
Wherein Q is...
Q is some formal parameter. Yeah. Well, you can think about it as element of your vector space C or formal. So let's write this matrix. I mean, let's write it down. To be very precise, very concrete. So it's a matrix from C2 tensor C2, so it's from C4. So you have like 1, 1, 1, 2, 2, 1, 2, 2, and also on this side. So let's try to write this down. So 1, 1, well, it goes to 1, 1, plus, when I equals j, I have q minus 1, 1, 1. So actually I have 1 plus q minus 1. So actually that's q, and nothing else. Where does 1, 2 goes, right? I mean, the matrix is like column by column is the image of these points. So 1, 2 goes to 2, 1, so 2, 1, plus something 1, 2. I is smaller than j, so it's q minus q inverse. Nothing else. Then 2, 1. Well, 2, 1 is pretty much the same thing, like it's 1, 2. But then 2 is in this else, so there's a 0, and then there's nothing else. And finally 2, 2 goes to 2, 2 plus q minus 1, 2, 2, so it's again q, and nothing else. It's a very concrete 2x2 matrix. So what have we to do now is we have to set this, I mean, we have to verify the Young-Baxter equation. So we have to compute two things. We have to compute, like to satisfy, to verify Young-Baxter. We need two things. First of all, we need R tensor I, the identity. This is what I call R12. So if you have two matrices, their tensor product, if you have A11, A12, tensor a matrix B, I'm not sure how to, which way it is, but I think it's A11B, A12B, and so on. So you just put matrices inside. Maybe it's the opposite.
Oh, is that one?
Is this one? I'm not sure if I did it this way, but okay. But then it means what? It means that. Okay, then I will start with 2, 1. Identity times R. It means that you put R inside the identity. It means that this is a matrix which is R, 0, 0, R. So here you really have to understand this is a 4x4 block, 4x4 block, 4x4 block. So this is an 8x8 matrix. Right? These elements, they are in GLV tensor 3. So here we have C2 tensor 3. It's in vector space of dimension 8. Well, so we can write this down, and R12 is the opposite R tensor identity. So now what you do is you actually take this big matrix and you add identities. You have Q times the identity. Identities on C2. So you have identity 2x2 matrix, then you have a 0, but it becomes the 0 matrix of size 2. And then you just do it everywhere. 2, 2, 2, you have 0, Q minus Q inverse identity. just plug in identity. I think you understand how to fill this in. So again, you have another 8 by 8 matrix. Well, now you see actually to what extent it's really not easy. This is like the simplest case. It's the simplest case, which is not just a swap map. And now we have to verify that composing this matrix with this one and then this again is the same as doing this. It's not obvious, but you can check. There's a very nice web page which is called Matrix Calc. I don't know if you know it. I use it a lot. So on this web page, you can like very easily like define matrices, like even very big. 8 by 8 is no problem at all. You just enter these two matrices, and then you can press the button ABA minus BAB, and it will spit out that it's 0. So yeah, if you don't know the web page, yeah, have a look. It's a really nice web page. You can do a lot of stuff there. You can also transpose. Of course, you can compute the determinant. You can decompose like LU or like this kind of Gauss decompositions. And what's really nice, you can also use indeterminate. Like yeah, you can. It does like formal computations. And it's free. I mean, you just go on this web page and nothing to download.
Is there some sort of motivation for why this would satisfy the young?
Yeah, okay, this is actually somehow the remark I wanted to do. Yeah, like why, or what's the general picture of this? Yeah, remark is, well, more generally, actually, you can take V, like more general. You can take V C to the N, with some basis V1 to the N, and you take exactly the same definition. Take the same definition here. Maybe I like this in color because it's very kind of universal. This thing together with this. Together with this. This stays the same. Somehow in this definition we have not used that it's C2, and this also works. More general, this like with the same definition. The same definition for R works. Well, this is harder because, I mean, even mathcalc.org will not work if n equals to 100 or something, right? And even more generally, actually, there's kind of a way to produce R matrices from what's called a quantum group. Yeah, we'll not give more details, but yeah, the main source of R matrices are quantum groups. The quantum group is not really a group, but it's some algebraic object for which you can, in particular, define a representation. So some action on a linear, on a vector space. And like for a quantum group, when you have representations, in general, when you take two of them and you tensor product them, then they are not isomorphic or not canonically isomorphic. Yeah, to their swap. Somehow, well, I've not given any definition of what this kind of representation looks like, but these two are not canonically isomorphic. But when you choose an R matrix, then they become isomorphic. Somehow the isomorphism between these two, this kind of swap map, is exactly given by an R matrix. So if you want to know a little bit more about quantum groups, you can actually go to my YouTube channel. It's in French, but I think there are English subtitles which are okay. And there's a video on quantum groups. Yeah, video. I mean, in general, it's a very good YouTube channel. You can completely neutral to it. For example, for those who were here last year, I did a lecture course on symplectic geometry. There's also a video on symplectic geometry.
In the TQFT picture, then, do we always have identical vector spaces on each of the?
Yes. Yeah, because like the points are all the same, right? TQFT associates the same vector space to the same manifold.
Yeah.
That's why you have all the same vector space every.
So like from the physics perspective, if we were considering like different particle types, is there a way to?
That's a good point. Yeah, if you want to consider different particles, what does it mean? Yeah, it does not really enter this picture then, or maybe you can enhance it, like doing more than orientations. Like if you label them, maybe, or if you take some grading, maybe you could imagine such a thing. But then things become much more complicated, right? Then you would have like a R matrix for any type A and type B thing which cross. Oh yeah, and one last remark. You can check. Well, it's not that important. You can check that if you take this matrix, or even the more general one for C to the n, you can check if you compute it square. Actually, it decomposes very nicely. It's actually a linear combination of itself, the matrix itself, and the identity matrix. And so somehow you see when I put Q equals 1, so Q equals 1 means actually that all these things are 0, so it's really just the swap. And the swap, of course, is of squared the identity. It's the swap. So literally what we have done here is you take the swap and you deform it. Add this one extra parameter. And the relation that R squared equals identity gets itself deformed. Okay, so maybe just to sum up what we have done, short summary is that, well, a TQFT somehow, a TQFT gives you a representation Bn to GL B tends to n for all n, actually. Like giving one solution of, I mean, let's say. You just solve once and for all the Young-Baxter equation. You find one solution, R, and this allows you to define a representation for any braid on n strands. And the idea is exactly what we've done all the time. Like you take your braid, very complicated. Take your braid, and the associated map is exactly this kind of scan. You see R here, you see an R inverse there, you see an R here, and so on and so on. You just scan through the braid, it gives you a linear map. And again, this Young-Baxter equation is assures that the braid relation is satisfied. Like if you take two different braids which are isotopic to each other, then you get the same linear map. Say it again?
This is how we consider topological invariance.
This is, I mean, well, this is, well, as it is for now, it's a way to represent these braids as matrix. And now, do we want to do it now? I mean, well, actually it's exercise 4 in this exercise sheet. In exercise 4, we want to construct, we construct link invariants from these. So I will just give you some more information in order for you to do the exercise. this is kind of the summary. Like a TQFT in this setting is exactly, I mean, only if no. It's like a TQFT gives you such a representation. There are other representations which are not of this R matrix form. Yes.
So the group homomorphism you wrote down before to the symmetric group.
Yes.
Could you then compose that with the group homomorphism from Sn to GL Vn?
I mean, you have a map here.
Factor, basically.
No, I don't think so. Because in Sn, I mean, if it factors, I think it factors if and only if R squared equals identity.
Yeah.
So, yeah.
Is that interesting?
In general, it will not factor through this.
Okay, thank you.
But you can also consider pure braids. So if you have pure braids, you also have a homomorphism. And, I mean, pure braids, they just map down to the identity, and for sure you will not get identities for these.
What does Q represent physically?
I mean, sometimes people would say Q is something like e to the h bar. H bar is small, so this is close to 1. But I'm not sure. I mean, in general, not clear. But I mean, yeah, in mathematics, very often when we deform something, we do not deform from 0, we deform from 1 somehow, so it's this kind of relation. But yeah, I don't have the more concrete answer. Yeah, so there's one final fact which I found really cool and I want to share, which is, I mean, if you want to go from braids to links, what we saw is that you have this closure, this closing procedure. The head over. And actually, so what we saw yesterday is that these objects. So now I read from top to bottom. So it goes from K to V, and so V star. So this is what we call the co-evaluation. And remember, it was just given by 1 goes to the sum EI tensor EI. And there was this other one, which goes from V star tensor V to K, which is this evaluation map, which to a linear form and a vector associates the evaluation. So now if I take my R matrix TQFT and I combine it with these two things, then I can actually now read off this picture. I can use this to read off the picture. And now, since this is kind of a closed picture, well, it's a map from K to K, and there's a nice proposition what this element is. Proposition. Let's give this map a name. Let's call it rho. Yeah, maybe rho. Rho is this R matrix representation. And so what we called D yesterday is this map from, this is a map from K to K, but it's really just number. So reading off, using the TQFT, the closed braid, this will give you simply, well, you take your representation of theta, this is some big matrix, and it's literally its trace. So this is something which happens a lot when you do these diagrammatic pictures, also in other contexts. When you close things up, you take traces. And the proof is pretty easy. Is this statement clear? What the symbols mean? This is the matrix associated to my braid. I take its trace, so I get a scalar. This scalar is the same thing as using this TQFT reading of this picture. By the way, we had one example yesterday, maybe do the example first. Yesterday we computed V of the circle. And what we found was the dimension of V. Remember? The dimension of V, I mean, what is the map associated to the trivial braid? It's just the identity. So this is literally the trace of the identity. So this is the case. So for the proof, well, I will write it like this. So let's beta, and I will just write one string because, well, this one string, what is written on it is W. W is just V tensor M. And so I consider a basis Wi of now W. So actually it is a basis of the form V. I mean, you have like just n tuple of vectors, basis vectors of V. Yes.
V beta hat of 1, like, because then it's a morphism.
Yes, okay. I mean, this is a homomorphism, and via this identification, I identify it to one number, and this is the trace, yes. Yeah, if you prefer, you can make, like, evaluate it at 1. Okay, so I take, like, all my vector spaces, V tensor V, I just call it W, just to make life easier, and you have this basis. And so if I read this picture, like, maybe I draw it again a bit bigger. Bigger. That's literally what we do. It's exactly what we did yesterday. We draw this picture and we read it. We read things off. Beta. This. So we have K. So then let's make the orientations. So I'm going up. So I have W tensor W. This is here. Then I have beta. So beta is just some map on this W component. So actually, I have beta tensor identity on omega star. Here I have the coevaluation. Here I see, well, W star. And then I go to K via the evaluation. Right? Coevaluation, which is kind of this creating of particle-antiparticle. On one hand, I have beta. On the other side, nothing happens. Then I have evaluation. If I write it down, 1 goes to, well, coevaluation by definition is Wi. Then I apply beta, but just on one side. And then I do evaluation. So this is co-evaluation, beta evaluation. So evaluation is simply sum of this. And this is literally the trace. You take the ith column and then ith intersection with the ith row. This is literally the trace. Well, trace of beta, well, probably I should write row of beta somewhere. Yeah. Actually, everything is row of beta. Because beta is really just the braid, row of beta is this linear map. Actually, if you compare this proof to what we did to compute just the unknot, I mean just the circle, it's pretty much the same. Just you have a beta, an extra beta. Any questions? Yes. So somehow exercise 4 tells you the following. So if you want to construct link invariants, what do? First of all, you use Alexander's theorem, which tells you that if you have any link, you can represent it as the closure of some braid. And then you can, for example, do this. But you have to ensure one thing. You have to ensure that when you take two different braids giving the same link, the associated invariant gives you the same thing. And there were these two Markov moves. One was you replace beta by beta, gamma inverse. And somehow what we do when we close, we just take the trace. So this is good, because trace of beta is equal to trace of gamma, beta, gamma inverse. This is okay. But what, I'm not sure if you redo it or if you just say that it's not true, M2 is not true. Like if you take, it's not satisfied. It's not satisfied. So if you take literally this R matrix representation of braids and you just take traces, you do not get immediately a link invariant. So you have to slightly change the construction. Well, and in this exercise I give like the formula. You have to introduce some small matrix mu. So you have to somehow, in this picture, you have beta, you close it. And what you add some kind of a bubble, which is a matrix mu tensor n. You add some matrix here, which has some properties. And then you cook up some expression which is on the exercise sheet, and this actually gives you a knot invariant, a link invariant. And as main source of like how this is defined, this is Turaev's paper. It's in the reference. This is the point number 5. Now Baxter equation invariance of links. And actually in this paper, Turaev shows that when you do this kind of construction, you get a link invariant which is as strong as what's called the Humphrey polynomial. The Humphrey polynomial is a slight generalization of the Jones polynomial, so it's really a link invariant which is pretty strong. So the idea is that you give me a link and I associate some polynomial to it. And yeah, sometimes if you have two links and you compute this polynomial, then sometimes they are different, then you really know that these links are different. But unfortunately it happens also that you have two different links and they give you the same polynomial. Then you cannot really tell. For now there's no invariant, there's no total invariant which distinguishes all nodes.
So shouldn't there be a row in there? Trace of row beta.
Yeah, sure. All there should be rows everywhere. Okay, questions. This was part 3. A little bit of delay. But it's okay. I mean, I really like this subject. Links, knots, braids. It's a great subject. So. If not, then we can go to the last part. Well, it will be shorter at least. Part 4, so it's another kind of application, generalization. It's like a 2D open and state sums. So that's a little bit of the idea from physics, from statistical physics. Yeah, we can really forget about all these links, braids, and stuff in another setting. So we come back. Let's come back to 2D TQFTs. What we saw yesterday is that these 2D TQFTs, well, you have these elementary cobordisms, creation and multiplication, co-multiplication, stuff like this. And the algebraic content finally was this commutative Frobenius algebra. And now I propose another building block, another approach, another building block. yesterday we had these kind of pair of pens. Sometimes the people use a pair of pens because the input and output. Now my basic building block now is a triangle. So really the idea somehow is, but actually kind of common in topology, when you have a manifold, is to triangulate it, to take like a cellular approach. So we'll take triangles and you glue triangles together in order to get surfaces. Why not? And so the idea somehow is that a triangle is still some kind of multiplication. If I associate to an edge some vector space, then I can, if I read it here from left to right, I have a vector space here, and then another vector space here. So I can interpret it actually as a map from V tensor V to V. So this is also kind of a multiplication. But now actually you should maybe first ask, well, but what's the triangle actually? Triangle is not really manifold, right? So the problem is that a triangle, well, it has zero-dimensional things, right? It has zero-dimensional cells, points. One-dimensional cells, edges, vertices, and, well, a two-dimensional face. So what I wrote here somehow is I want to associate vector spaces to edges. So I'm in the 2D setting. So the TQFT, it will associate vector spaces here. It will associate linear maps here. Well, what should we do with what should we do with the points?
Scalars? Scalars?
No, it's radical. We just remove them. Just remove them. So it means that actually in this picture somehow, maybe I will not draw it like this, but actually I should actually draw it maybe like this. I'm not considering it. They are off. So it means in particular that we are not working with closed manifolds anymore. We have now open manifolds. That's why it's called an open TQFT. Now we have open manifolds. So of course, I mean, we have the same kind of discussion. We can have the same kind of discussion as earlier, like how do we distinguish like incoming and outcoming edges? But this is the same as for usual 2D TQFT. You can introduce orientations and then say, well, there are some orientations which are incompatible. These are the incoming ones, and some others which are compatible on the boundary. They're the outcoming ones. So skip this technical detail about the orientations. I think you have a good understanding of it now. And so there's one really interesting remark, which really shows that it's different from the 2D usual TQFT, like difference to usual 2D TQFT. The big difference now is that this multiplication is not commutative. Multiplication is not commutative now. Let's draw the two pictures. The two pictures of the two multiplications. So if I put H1 here, H2 here, what put H? Okay, for some reason, yeah, no, let's call it V. V1 here, V2 here. Then on this edge I will see the multiplication, V1, V2. So maybe for once I will write the orientation. So if I orient it like this, then I will have compatible orientation and not compatible orientation. If I draw the similar picture, it's V2, V1, V2, V1. So now actually the orientation can actually help, because it's something like going from here, well actually this point removed, but if you go from here to here, you see V1, V2, and it's the same as going from here to here, so you have V1, V2, here, V2, V1. And actually now you can check that these two things are not homotopic. I mean, they're not homomorphic one to each other. If you turn this around, well, then actually V2, but V2 will not match to this because I think the orientation does not match, right? Yeah, orientation does not match. So actually these two things are not homomorphic. And so a priori this multiplication is not homomorphic.
So now we get rid of all of the pans and we build the whole, like a complex out of these triangles?
Yes, exactly. I mean, I will define the object, we will glue triangles together and we'll see what. But maybe, let's see, as a remark, so it's not commutative, but it's still associative. So can we see this? So if I draw V1, V2, this is V1, V2, so now I should multiply this by V3. The arcs because it's easier. So I have V1, V2. Now I do V1, V2 with V3. This should give us this thing. This is V1, V2. This is V3. So here now I have V1, V2, V3. And I think, yeah, if I take the same picture, but I triangulate things differently, I just triangulate like this. Literally do the same thing. Then I have V2, V3, V1. Here I have V2, V3, so I have V1, V2. And these two pictures, of course, logically, if I take an edge here or here, it's the same. This is actually pretty amazing, this fact that associativity corresponds to what is called a flip. So the flip is a change of diagonal in a quadrilateral. In this quadrilateral, you have V1, V2, V3 as a product. You cut it somehow this way. Again, kind of this, yeah, it's again the TQFT perspective. You have V1, V2, V3, you read through it, and now I want to decompose it into elementary pieces, but I can decompose it like this, or I can decompose it like this. And the fact that it does not depend on this choice translates into some property of the multiplication, which here is associativity. Yes.
Is there a reason you're reading these products from left to right? So V1, V2 is first V1 and then V2 as opposed to...
No, but I think you can really use the orientations. Like going from this point to this point, you can either go here or here. Mm-hmm. I mean, if you prefer, you can like always orient things in the same way, and then you can speak about loops. You have kind of a monodromy, but you have like trivial monodromy.
Writing V2, V1 instead of V1, V2.
Okay. Oh no, I see what you mean. Yeah, sure. Yeah, if you think this as composition of maps, I should write it the other way around. Yeah, but here it's well, yeah, you could. It's true. But here it's more like it's not really a map, right? It's a vector. Yeah, it's vector multiplication and not composition of linear maps. Okay, so somehow when we draw these triangles, well, for me, a triangle seems much easier than this pair of pens. You get the same kind of TQFT picture. You get again an associative operation, so it's very nice. Yes.
Sorry, I don't understand the red arrow and why it goes in the opposite direction as V1, V2. I mean, V1, then V2.
So all the arrows I draw here is like a TQFT gives, like, it comes with oriented things. For example, here I take the triangle with this orientation, and I consider its boundary with this orientation. And then what we saw yesterday is what is incoming, what is outcoming. Outcoming boundaries are those such that the induced orientation coincides. So here the induced orientation, I can write it in red. The induced orientation here goes up, it goes here, and it goes here. So when it is aligned, then it's outcoming, and if it's against, then it's incoming.
So it's because it's the input.
Yes, input output. Yeah. But again, you can just change the orientation, but then you replace V by V star, and you just use this kind of canonical isomorphisms between V and V star.
So it's not isomorphic. I mean, for me it is homeomorphic, but not homeomorphic with an orientation preserving homeomorphic.
This? Oh yeah, sure, yeah. But whenever that was a question yesterday. Whenever I say homeomorphism for TQFTs, it's always preserving orientations, because really we work with the category of oriented manifolds, so you take homeomorphisms in this category. Yeah, you're right, yeah. I can just turn it around, but it will not respect orientation. Okay, so now we have a new way of playing around. We have now new building blocks, and let's just put them together. And what we get is what is called sometimes a ciliated surface. So the question we could ask is, what kind of geometric object? What geometric objects can you build from gluing triangles? Seems such an easy question. It was like one of the hardest questions when I prepared this lecture to figure out like all these degenerate cases.
If you draw the last green arrow in on your associativity thing, is it not going the other way?
So it's always the same. It's like this. Yeah. Okay. If you forget the interior, you have exactly the same boundary data. The TQFT somehow tells you how to decompose in more simple pieces, but it should not depend on this choice. Let's give you the same case. So what can you get when you glue triangles? Well, let's give them some examples. Well, of course, you can get polygons. Right? You can like take a triangle, glue it to some other triangle, and just keep going, and at some point you stop. What you see is a polygon, triangulated polygon. You can also imagine, I don't know, starting from polygon and just triangulate like this. Well, actually, there's a slight difference between these two, because what I said is that the points, we remove them. So here I have a polygon without vertices, and here I have a polygon without vertices and one extra point in the middle I removed. Polygons with potentially removed points in the interior. What else can I get if I glue triangles?
Surfaces?
Surfaces, yeah. Let's do, for example, two triangles like this. You glue them together, and then I identify this with this, and this with this. This is why it's so hard, because you can actually like glue things together. So this is homeomorphic to what?
Torus.
Torus. Again. Torus. Another picture is almost the same, but now you glue this to this, and this to this.
Klein bottle.
So even for the torus, I should say one more thing. How many marked points are on the torus? How many points I have to remove from the torus? One. Exactly, because this point is actually identified to this point via the green, and this point is identified to this via the red, and then again here. So you have one marked point on the torus. So this is sphere, yes, if you just identify these two things and these two things, that you just close it up, it's a sphere indeed. How many mark points? So how many points are there? So this is one point. This point gets identified to this point, and this point is the third one. So yeah, there are 3 points in this thing. And it goes on, so you can do a lot of stuff. Just some ideas what goes on. In general, what you get is exactly what is called a ciliated surface. Yes.
When you remove the points, do we just consider them non-terra, or are these punctured surfaces?
I mean, in the first, if you just look at them topologically, actually what a puncture is has no meaning. Yeah. So topologically, it's really you remove the point. Okay. But if you have hyperbolic geometry, then you can put on what I will define as a ciliated surface, you can always put a hyperbolic metric such that all these points are cusps. Cusp, or as you will see, you can have marked points on the boundary, but then somehow on the boundary you also have a cusp. So these points, they are infinitely far away, which means that you can, even if you have these removed points, you can equip these surfaces with a complete hyperbolic.
So like the way that we have polygons and we go to identify edges, could we extend the previous theory of braids to links in the same way? Could we think of the torus as some kind of link of a braid?
Oh, you mean you want to define polygons and then you do a polygon gluing as the closure of a braid? Yeah. Maybe. I mean, it's true that any closed surface, any closed ciliated surface functions will be fluid from such a thing. Yeah, so kind of yes, but it seems still different. But it's true that a TQFT will build at the end, if you have a closed surface, it will be just one number. And what it is, if you represent your surface as a gluing of a polygon, then it's literally the trace of what happens on the boundary. So it's pretty similar. Okay, so let's give you the definition. I mean, it's not very illuminating, but it's a surface. It's a closed. I mean, it's a surface in the sense we had yesterday. So closed, compact, oriented, connected, and so on. So it's a surface as yesterday, from which we remove stuff, from which, with potentially boundary, no, from which we remove. A finite number of disks. Maybe I should draw the picture first. First draw the picture and then you can read off the definition. So a general ciliated surface looks like this. You can have genus, you can have boundary of components. But on boundaries, you always have at least one marked point. You can have more. And in the interior, you can also have marked points. The marked points somehow are the removed points somehow. So you start from somehow this picture without the red dots and without these disks. So you start from this closed thing, then you cut out disks. This gives you the boundary components. And then you add these marked points, some number of disks. And I remove and at least one marked point. In the interior or at the boundary. Okay, let's see. And at least one marked point, yes, in the interior. Or at the boundary. and at least one marked point per removed disk. Per removed disk. So it means two things. So whenever I remove a disk, I have to mark at least one point. I can additionally remove points just like this. But it is actually possible to not remove any disk. But then what the definition says is you have to mark at least one point. Like if there's no marked, if there are no boundary components, then you need at least one point.
Yes. So you remove the mark points.
Yes.
And how do you then it becomes the same as if you remove a disk topologically? How do you differentiate?
Okay, so you remove an open disk, so the boundary is part of the surface, and then you remove additionally these points. Yeah, that's a good point. Wow. It's, you remove open disks. And so now what I call the boundary is literally these arcs at the boundary. So the boundary of a ciliated surface is a collection, is a disjoint union of arcs, of intervals. Disjoint union of intervals. Yeah, intervals. And so our TQFT, it will associate a vector space to an interval. But since any two intervals are homeomorphic, it will always be the same vector space. And it will associate some linear map to any ciliated surface. And somehow the fact, which you can prove, but it's actually almost by definition, is that any ciliated surface allows a triangulation such that the vertices of these triangles are exactly the mark points. The vertices are the mark points, and only the mark points. So that's why it's so important to have at least one mark point, because if you don't have any mark point, then you cannot even start doing any triangulation. Okay, so again, like it seems so easy. You just take triangles, you glue them together. But let's see the examples. I mean, we are already in this TQFT perspective, so let's try to find the easiest ciliated surfaces. Because ciliated surfaces are these linear maps, so we want to decompose them into elementary pieces. So we should ask what are the simplest possible ciliated surfaces. Actually, it's harder than you might think. Well, of course, you have the triangle. For example, let's say the elementary, or maybe just the easiest examples. Well, we have the triangle, literally just the triangle. But actually, that's even easier with the triangle. It kind of seems strange because we build things from triangles. How can there be something easier? We can have the one gon, which is simply one marked point. I mean, it's a two-dimensional thing, right? It is also two-dimensional. How do you get this from a triangle? So here what you have is actually, you take, for example, a sphere, you remove one disk, so you have one boundary component, and you mark 3 points on that.
Can you identify the three?
Yeah, exactly. You have to write this as a triangle, but then we have to identify stuff. For example, if I identify this with this, okay, you can imagine I glue things together, but then how many marked points do I have? I have this one, and these two get identified, so this is not good now. We have to identify even more. For example, we can identify this and this. And then you get this. So we can also have a two-gon. Two-gon is actually, we actually produced it on the way of producing the one-gon. This thing is the two-gon. That's funny. I produced the two-gon differently. Is this a two-gon? Yeah, it is. Okay, there's another way of producing the two-gon, which is using two triangles. Okay, so to identify these, then you identify these, and these, and these. Well, apparently this also gives you the two-gon. And we will actually use this.
Isn't that a cone?
The cone is also there, but not this one, I think. There's also a cone, you're right. Actually, yeah, it's really amazing how difficult these things can be. Oh, how easy it is. There's also the cone, the one punctured cone, so you have like, well, you have a point here, you have one boundary component, and so on each boundary component you have at least one mark point. So it's like, yeah, the cone with one mark point on the boundary. But you have also, well, one mark point in the interior. So how do you get this as a triangle? Oh yeah, you're right. No, this is actually this picture. This is the cone. You're right. Yeah, no, you're right. This is this. Thank you. Why actually? Because when you glue these things together, you get one boundary component, which here you have one boundary component with one mark point, and you have one point in the interior. So if you prefer, I can write this as simply the disk with one point on the boundary and one point in the middle. Okay, very good. Thank you. So this is wrong. This was wrong. This was not true. No, just remove it.
For the one-gon, I thought this identification is how you get the topological dunce count, dunce hash. If you've seen this shape.
Well, this is like the disk, and you identify you identify diametrically opposite points. This is different here. You really identify like this point to this point to this point. You have triple identifications here.
Yeah, but I still thought that was the. It's possible the marked points make a difference. Maybe when you remove them.
I don't know. Literally, if you start here, you go along, then here you come back. And then somehow if you go around this triangle, then you just do this 3 times. So literally, this is this. Oh, so actually, I gave you the result, but this is actually a really hard exercise to get the two-gon from triangles. Well, actually, I should not have given you this answer, but two-gons is difficult. And actually, what happens in the two-gon, if you really carry this out, is actually the following. That's why it's really a bit mind-blowing. It's actually this. So you have a one-gon. So a one-gon, we know that it exists. It's here. This is the one-gon. And what we have here is actually a triangle, because you have 1, 2, 3 edges. And so you glue this triangle, which already is kind of degenerate, to this one-gon, and then you get the two-gon. And this is literally what happens here. This is the one-gon. This is the this is actually the cone. And so you glue, yeah, exactly. You take actually the cone and you glue a one-gon to it. Oh, it's nice. Oh, I haven't seen this. This is great. So actually, you should say that the one-gon is the easiest, then comes the cone, and when you combine these two things together, you get the two-gon. Yeah.
Does it work with like 3-gon, 4-gon?
I mean, the 3-gon is the triangle, and then it's actually easy, right?
Oh, yeah.
It's really the one-gon and the two-gon which are hard. And the last one, which is not that easy, but it's not that difficult, is the annulus. So an annulus looks like this. This is the interior. And since you have two boundary components, by the definition, you need two mark points. So how do you triangulate this stuff? So you can also triangulate this. Remove these things. So, how do you triangulate this? So you can add an edge here and an edge like this. And now you can see that there are two triangles. One triangle is this one. It has 1, 2, 3 edges. So you take the boundary as one of the edges. And the outer one is the same. Like 1, 2, 3. You have two triangles. Each triangle is already degenerate and you group them together. So just to give you a feeling like how complicated these objects can be. A lot of time left, so I will be a bit quick now. So what we have is, well, if you want to define a TQFT on these objects, on these surfaces, so what you have is, sorry, question?
Yeah, so this question for the annulus.
Yes.
Yeah, can we say it is homeomorphic to a cylinder?
Sure. Yeah.
Because
it's a cylinder with two boundary components. Yes.
Because it is a disk multiplied by an interval.
Yes.
Yeah.
You can take a disk and you look a cylinder. You look at it.
Yeah. So if it's like homeomorphic to a cylinder, what if we do the square representation of the cylinder and the triangulation becomes very easy?
Like, okay, that's a good point.
This.
Yeah. If you do this, you have two triangles. And now you just glue one thing together.
Yeah, it's a cylinder.
I think you're right. Yeah. This is, if you do this, you should get this as well. Because you have two arc points, you have two boundary components. Yeah. Thanks.
We can do that.
It's much more. I think people. It's easier to see here than here.
Thanks.
So now what happens is, when you take this TQFT perspective, well, we have an interval. All intervals are homeomorphic, so we'll get some vector space. And then all these kind of elementary examples, they give you some operations. So the triangle equips this vector space with some multiplication, which is associative. And I think you also have a unit. And there's one more structure with respect, like comparing to 2D things. There's one more thing, which is the one-gon. Actually, the one-gon, how should you read it? The one-gon, it's a map from the vector space. If I draw it like this, how should I draw it? Maybe like this. Then I kind of imagine it a bit like a cup. If I read this from bottom to top, I see my vector space, and here I see nothing. So it's a map from V to K. So there's a map, and I will call it a trace. It's a map from V to K. And actually now you can combine the multiplication with this trace, and you get a Frobenius structure. So you can actually define, I think I call it sigma of AB. You can define it as trace of A times B. So it gives you actually a Frobenius structure. So this kind of TQFT is a particular case. Gives a Frobenius structure, Frobenius algebra structure on V. But it's a bit different, because if you remember a 2D, like the usual 2D TQFT, they were in bijection to commutative Frobenius algebras. Now we have seen that this thing is not necessarily commutative. So you might say, well, maybe you have a bijection now to non-commutative Frobenius algebras, but it's almost true. It's a bit more, because you have one more property, which a priori is not true in a general Frobenius algebra. One more property, which is the following proposition. trace of AB equals trace of BA. So multiplication is not commutative, but when you apply trace to it, it is. So I think it's the last proof we will do. It's a really nice proof. You just have to draw the pictures, as always. So what's the picture of this? So I have A times B, and the trace is somehow gluing in this thing. A B with A times B, and then we trace. But actually, if I want to be exact somehow, I should do it. I should actually write it like this. Because when I do a multiplication, I need a triangle. So here I have my triangle. It goes from here. Oh wait, no. Here. Right, I can go from this point to itself via A, B, or I can go just around this loop and then I have A times B. I use somehow this triangle here. And then trace is gluing in, it's actually exactly this picture, gluing in a one gon. So I start first from this triangle, and then I glue in this triangle next to the trace. So what I have to prove is that this picture is the same as if I turn things around. So now I draw the same picture. I put B here, A here, and I will have B times A. Actually now you can convince yourself that this is literally a rotation by 180 degrees. If you take this picture, turn it around, you have B going up, A going down, and this still turns this way. So this, of course, the rotation is topological equivalence, so it gives you exactly the trace of AB equals trace of AB. So maybe, yeah, I will shorten the rest. So as a summary, what we should say is that a 2D open TQFT on ciliated surfaces is actually in bijection with what we call, well, an algebra. Algebra means it's a vector space with some multiplication with a symmetric trace. So trace is this kind of function from V to K, and symmetric means exactly this. And yeah, so now we have somehow, I mean, we have not proven anything, but there is a difference between these.
You mean a Frobenius algebra or any algebra?
An algebra with a symmetric trace is a particular example of a Frobenius algebra. In particular, now we can have non-commutative things. So it's both more general, but also, I mean, you have like all Frobenius algebras, you have commutative ones, these are the usual TQFTs, and you have these symmetric cases where you have these open TQFTs. Okay, then I had actually some concrete examples. Oh yeah, I have not spoken about the state sums. Yeah, well, okay. I mean, there's also some statistical mechanics a bit behind, because when you take like a ciliated surface, you triangulate it, but how do you really compute things? So if you really want to compute things, you will like fix some basis of the vector space. And then what actually happens is that for every triangle, you can associate some number. So if you have a whole surface, then you will actually sum over all possible labelings over the edges and take then the product over all of these triangle numbers. And this is typically something you do in statistical mechanics. You sum over all states, and each state is a product of like individual factors. So maybe I will just write this remark. To compute anything like invariance, for example, this TQFT, this open TQFT, what we use is this kind of state sum. We use state sums like from statistical groups. Okay, and to end on this, select this. So, just at the very end, I just want to give you a list of things you can still generalize. I mean, you can of course generalize a lot of stuff, but just to give you some opening. So there's a lot of stuff you can do. Well, even in 2D, we have not completely finished because we have seen kind of these closed TQFTs, where you have like these pair of pens and stuff. Here we have seen open TQFTs, where you can remove points. And there's actually something called an open closed TQFT, like even in 2D. So it's somehow an object where you can combine ciliated surfaces with usual ones, so you can actually now have boundary components like this, for example. This will be an open, closed TQFT. And then you have actually two different objects, because now we have two kinds of boundaries. You have circles, and you have intervals, and the circle and interval are not homeomorphic. So now you have actually two different things, a vector space here and another vector space here. And each of them has a certain structure. I might lie, but maybe this is kind of this commutative Frobenius algebra, and this is kind of this symmetric algebra, and then they also interact. So it's actually kind of interesting, but also kind of a bit complicated theory. Then there's, a really cool thing I wanted to say is there's a notion of an extended TQFT. It's pretty cool, because earlier, I think I raised it, I said that, well, the problem with the triangle is that you have like 0-dimensional stuff, 1-dimensional stuff, and 2-dimensional stuff. But actually, and somehow we decided to throw away the 0-dimensional stuff. But actually what an extended TQFT is doing is that it will associate typically, well, for example, in 2D, for example, in 2D what it will do is like to points, like to 0-dimensional things, to 0-dimensional manifold, it will associate a vector space. Then to 1-dimensional things, it will associate linear maps. But, well, what can you do for 2-dimensional things then? Well, it's somehow a linear map between linear maps. So, it's kind of, I don't know, a natural transformation or something. Or it's called an intertwiner, I think. Intertwiner. And actually, at this point, it's actually a bit better to switch to a categorical language. So actually, from the very beginning on, you could ask actually, why do we always speak about vector spaces? Actually, you can use much more general things, which are called categories. So associate objects to things, and then morphisms to cobordisms, and then somehow you can define like the notion of a morphism between morphisms, which is called a two-morphism. So this somehow would constitute what is called a two-category. And more generally, in ND, you can have an n-category. So yeah, so this is actually a very nice kind of generalization where you're not only playing with linear maps, but also between like relations between these linear maps. Okay, maybe at the very end, so there's also like CFT and something called CoFT. I mean, a lot of things which are more restrictive than TQFT, but you still have this kind of same kind of idea. You have boundaries, you have some cobordisms, and typically we will put more structure on the cobordisms, but kind of these axioms always stay the same. So I mean, just this idea of TQFTs is a very general idea, which you can, pretty much encounter a lot in a lot of settings. And yeah, I think with this, I can stop. And thank you for your attention.